Hello everyone, welcome to the new Deep Learning and Reinforcement Learning module. For those of you who don't yet know me, my name's Chris Wilcox, and my passion is really artificial intelligence and deep learning, where a lot of my research group is just focusing on theoretical, foundational areas of this field, looking at generative models, unsupervised learning, meta-learning, reinforcement learning, and so on. So just a little bit of administration. We'll be having 20 hours worth of lectures, and approximately every Monday we'll be having a deep learning lecture, and every Friday I'll release the reinforcement learning lecture. And the coursework is already available, so you can access that early. However, I really do recommend that you spend your time to take things slowly at the beginning. You do lots of reading at the start and sort of really try and build up your theoretical knowledge of the field before jumping in with the coursework. So maybe after sort of 3 or 4 lectures in, then you can start to have some ideas about the coursework. But it's nice to just see what's there, so you might get a feel for where we're going with this lecture and module series. So this is a newly revised submodule. Every year I have to completely redo most of these lectures just because the field is changing at such a rapid pace that even since last year, many of the state-of-the-art methods are now replaced by new state-of-the-art methods with completely different techniques which are just far superior. So even this year, even in the last few months, major changes have happened within deep learning, which have led to some very exciting developments. So we'll be trying to come up to pace with where things are all going. So in this first lecture, it will be a very gentle introductory lecture where we're really going to just look at the concepts. And we'll start with just some definitions of what learning is and what deep learning is. And we'll study how learning works in nature, how we've evolved to learn, which really involves looking at the human brain, getting to see the architecture of the brain and the fundamentals of the brain, and then the kind of mathematical models we build from those fundamentals. And we'll look at the actual theory of how learning in the brain works. Then we'll go through a history of deep learning. And history is very important in this field because as we look back, going back many, many years now, we'll see how techniques have evolved and developed, which actually helps give us a bit of future-looking foresight to see where things are going. And it also helps lay a foundation to appreciate how these concepts are changing. And lastly, we're going to finish with just actually looking at some of the main concepts. But because I assume you've already done some machine learning content, this will mainly just be a brief slide or so just to say what the differences are between machine learning concepts and deep learning concepts. Okay, so with that being said, let's actually just talk about some of the aims of the entire module. So the way I'm going to teach this is a very kind of concept-driven, hands-on approach, where you're going to be learning a lot of the practical and useful techniques. However, in the first few lectures, there will be a solid theoretical foundation which is laid down for you to use as you read papers and self-study. But just reading this slide, the main aims of this course, the submodule Deep Learning, are that you'll be able to finish this and then go ahead and solve some very complex and ill-defined problems that require deep layers of learning. So you might have done some simple learning problems before, like simple regression problems or classification problems, but with deep learning we're really trying to solve much more ill-defined problems, things like detecting emotions or things like generating images given data we've never seen before, these kinds of problems, or studying very high-dimensional data sets, very, very large data sets, where you just can't get away with shallow learning. You need deep layers of learning. We're going to have some solid theoretical lectures where we're going to really understand the statistics and the geometry of what's going on here. We're going to also, especially in this first lecture, just look at how learning works in nature, how learning works in the brain, looking at other fields and other disciplines. So we've got this kind of broader picture of what learning is and deep learning is. And when you have finished this course, when you're given a new task, maybe by your employer or someone, you'll be able to approach this task with a rigorous scientific method where you'll be able to ask the right scientific questions given that task. You'll be able to think about the distributions of the task, the distributions of the data, how to map between those two distributions. And also, of course, you'll know how to use some of the state-of-the-art deep learning libraries, modern deep learning libraries, which allow you to do automatic differentiation and to use lots of pre-built tools to quickly develop a unique solution. But really, it's more important that you know how to ask the right questions when you're given a new ill-defined task with the underlying theoretical foundation to build on. So my approach to teaching this course is really going to be very much foundations first and then concepts and state-of-the-art techniques second. So you should notice a kind of shift in the lectures as we progress going on. So in the past, machine learning and deep learning fields have mostly been dominated by statistics and mathematics, but recent advances in the literature, surprisingly, things like capsule networks and meta-learning, they've actually been strongly influenced by psychology, by biology, and by nature in general. So new research is heavily dominating old techniques. So, my teaching style is going to be to try and encompass these modern techniques as much as possible, which involves ultimately being more conceptual, talking about the shape, the distribution, the geometry of techniques at a kind of high level. But we will dive into low-level areas of importance as well, such as the backpropagation algorithm. So there's kind of different ways you can approach deep learning. You can approach it from the statistical perspective. People like Christopher Bishop is quite aligned that way with his book. And also like Ian Goodfellow, if you've looked at the reading list already, you'll see Ian Goodfellow's book is kind of like some people call it the deep learning Bible, but it's quite a large book. It's getting a little bit dated now, but he also approaches the topic very much from a statistical perspective. But I do recommend his resources to just kind of scan through it. You can also approach deep learning from a geometric perspective. So you can talk about data sets as high-dimensional manifolds or surfaces in some high-dimensional space, and the actual learning process itself is some kind of geometric unwrapping of this or flattening of this high-dimensional surface into something simpler that we can understand. How the space itself becomes warped through various functions, deep functions. So it's kind of like a geometric view. Okay, so alongside deep learning, we'll be studying reinforcement learning. And reinforcement learning can use deep learning. And I'm going to go quite detailed into what reinforcement learning is, of course, in the reinforcement learning lectures. But I'm going to try and approach both of them at a kind of conceptual level with the rigorous theoretical foundations laid first. At the same time, you'll be having lots of examples and code you can run, which will help you to then go ahead and implement the state-of-the-art methods in a real-world and useful setting. So let's start with an actual definition of learning. And this is by Jan LeCun, Joshua Bengio, and Geoffrey Hinton. Now, these three people are sometimes called the forefathers of this field. They're really legendary people in the field of deep learning, and they've been highly influential throughout most of the recent history of deep learning. And if you just click the link here, read online, you'll see it links to this Nature paper written by the three of them. And actually, I suggest after this lecture to actually just have a quick read through this. This lecture probably won't be a full 50 minutes, so if there's a few minutes spare at the end, I would recommend you just take your time to read through this, and that will help give you another perspective from these three legendary forefathers into the field, how they see it. And it's a very easy, gentle read with lots of concepts and links to sort of see through. It's quite short as well. And that was published in Nature. So coming back to the slides now, let's just look at this definition as they say. So they say deep learning allows computational models that are composed of multiple processing layers to learn representations of data with multiple layers of abstraction. These methods have dramatically improved the state-of-the-art in speech recognition, visual object recognition, object detection, and many other domains such as drug discovery and genomics. Deep learning discovers intricate structure in large datasets by using the backpropagation algorithm. So if we kind of unpack this definition a little bit, you'll see the first thing is this idea of multiple processing layers or multiple layers. This implies there's actually some kind of hierarchy or progressive transformation of the data as we learn. Then it refers to the idea of learning representations. So you may be asking yourself, what are representations? And when you see representations referenced in the literature, you usually see these discussed as in terms of feature vectors. So representations are these kind of high-dimensional feature vectors. So we learn to represent or model complex data like images and sounds by these simpler feature vectors. And it's actually quite difficult to infer patterns from high-dimensional noisy data such as photographs. But if we can extract these feature vectors for that data, so for example, the vectors could be like whether the image contains a car or a pedestrian, then we can actually use the feature vectors to tell our system to avoid hitting the pedestrian. And to do this, we need to somehow simplify the data to a representation or vector which tells us where the pedestrian is. Also in the definition, they talk about across domains, many other domains. And the methods you do learn in this course will be extendable to many other domains, domains such as natural language processing, audio processing, computer vision, and so on. Now, most deep learning researchers believe that we're heading towards this kind of unification of the domains. So in the future, many researchers believe we're going to have one single large AI model which solves all problems in all domains, like human brains do very much. We can play musical instruments, we can paint pictures, we can solve many, many different problems with this one architecture. And many researchers believe that's where we're heading. We're heading to this unification of the domains under a single large, massive, centralized, deep neural network. And lastly, there's this interesting mention of this one specific algorithm, the backpropagation algorithm. So there's this fundamental algorithm which allows all these amazing things to happen. Right, so let's just have a look at some examples of deep learning. And I've already opened the tabs, but you can actually click through all of these links if you want to see the full videos. I'm just going to briefly go through some of these exciting recent examples. So this is from just training a deep learning neural network on a finite data set of images of human faces. And the neural network is able to actually learn a representation or feature vector representation, a latent space of the faces, where you can actually sample this space, this continuous space, to generate an infinite set of plausible faces. So I could stop this video at any time and you'll see something which looks like a realistic and plausible face, but actually there's an entire space of faces. So here's another place I would spot. That looks like a real person. So there's this infinite space that's captured where every point in that space, that representation space, looks like a realistic image or a realistic person. So this model has truly learnt the distribution of faces. It's truly learnt this data distribution of all faces. And similarly, here's another example. This time, instead of training on photographs of faces, it's actually trained on art styles and portraits. So let's just have a listen to this.
The image grid on the left shows a style map. Navigating this map results in artistic changes to the portrait. Stopping between two styles creates a natural-looking hybrid between them. We can see that the subject's identity, expression, and pose remain fixed as we change the painting style. The StyleGAN deep neural network learned to separate elements of style from aspects of content. This was accomplished using a dataset where every image was unique in both style and subject. Turning this incredible complexity into a fluid tool for image generation opens exciting new opportunities in a variety of industries. StyleGAN 2 offers creators and artists exquisite image quality and endless variation to bring their visions to life.
So with StyleGAN, or this deep neural network, it's learnt this space over this distribution over paintings, and you can sample any points between even paintings and styles and synthesize new paintings. So it's a very exciting technique. It has large implications to where maybe art might go in the future. Here's another negative application, I would say, because there's just been a lot of people have taken this research and applied it in various nasty ways. But nevertheless, it's still interesting to see what's happening.
Wrong a million times worse. Attacks cheat. What do? They take every penny. You go in the can for felony tax evasion. Ouch.
So in this application, people have taken Donald Trump. They've trained a neural network on faces and videos, and they've superimposed Donald Trump's face onto Saul Goodman from a TV drama. Why is this a negative application? I would say, well, yes, it's humorous, this video, but actually this has been applied in various really horrific ways, to be honest. So not all research always leads to a good outcome. So when you do research, I think it's important to always think of the implications of how your research might be used. Perhaps the slightly more positive application is from Alex Kendall in his company Wave. And this is actually a deep reinforcement learning algorithm, but it's using deep learning under the hood. So I'll just play this video. So basically, Alex is driving this small electric vehicle, and every time the vehicle does something wrong and Alex needs to correct it, the model learns not to do that again, and it tries to minimize the error from when Alex has to correct it. So it learns this policy to drive in all of these very, very difficult conditions. So you can see it's raining, there's a hazard approaching, and the vehicle is able to adapt to all of these different situations and dynamics. And that's learned all end to end, so it's a single model which has learned to do all of these difficult maneuvers and tasks. Okay, now we're going to move into deep neural network models trained in natural language processing. And this is an extraordinarily exciting model. You might have heard of it already in the news, called GPT-3. And this is a huge model trained on the entire internet. And it just goes to show that if you have a large enough model, it can actually start to generalize to not just one task, but an entire distribution of tasks. This is called a meta-learner because it learns to solve many, many tasks. Let's just look at the applications.
And it turns out it has read a lot of things on the internet which contains a lot of code, so it can generate website layouts from a written description. 2. It also learned how to generate properly formatted plots from a tiny prompt written in plain English. Not just one kind, many kinds. Perhaps to the joy of technical PhD students around the world. 3. It can properly typeset mathematical equations from a plain English description as well. 4. It understands the kind of data we have in a spreadsheet, in this case population, and fills the missing parts correctly. And 5. It can also translate a complex legal text into plain language, or the other way around. In other words, it can also generate legal text from our simple descriptions.
So I don't know about you, but when I see that and I look at the rate these models have come in the past couple of years, I'm extraordinarily excited. This is one model, and nobody's told it to be able to translate between legal text and English text. It's just learned by looking at the internet to do all of these different tasks. So the same model can translate between French and German and English. So it's learned to comprehend all of the languages it's seen on the internet. It's also starting to be able to do more difficult tasks like generating website code, or even generating its own code to run neural networks. And it works just by imitation. So this is kind of going back to the imitation game. I'll talk a little bit later about how these kind of language models work. And lastly, an application from audio.
Or, in other words, take a genre, an artist, and even lyrics as an input, and it would create a song for us. Let's marvel at a few curated samples together. The genre, artist, and lyrics informations will always be on the screen. Wow, I am speechless.
Me too. But I mean, how amazing is that this model has been trained on these songs, and somehow they've built this architecture where you can change the lyrics to talking about SGD, which stands for stochastic gradient descent, which is actually one of the algorithms we use. And it's able to generate a completely new song in the style of some artist, and actually you can interpolate between artists and get this space of new songs out from it. Very cool indeed. So deep learning has these remarkable applications, which you see about and hear about new ones all the time on Twitter or wherever you're following on the news. But let's take a step back now and sort of go from the basics of learning and build our way back up to those exciting applications. So learning in nature generally has this kind of pattern where there's this environment. So in this case, there's this nice, delicious ice cream, or there's this wood burner, and we, or the agents, experience this environment. So we might taste the ice cream and find it's delicious, we might find it's cold, or we might get closer to the wood burner and experience that warmth of it and the smell of it burning. But then the agent, we take some actions in the environment. We might put the ice cream in our mouth, we might get closer to the wood burner, we might touch it, and then from that experience we might change our actions. We would want to eat more ice cream, or we might say let's not touch that again, and that happens over time. So learning in a very kind of high level is this idea of changing your actions according to your experience of the environment over time. And when we build a definition of learning, there's actually many different subjects we can go to. We could go to neuroscience, we could go to education. For example, in education there's this wealth of pedagogical literature on learning. We could even go to sort of information theory and look at how information and signals are optimally transferred between systems. But we're going to start kind of at the neuropsychology level. We're going to look at the science concerned at looking at the brain and the nervous system, and then we're going to go to the mathematical models. So here's one definition of learning out there that I quite like. There's lots of ways you can define learning. There's huge numbers of definitions floating around on the internet, but I do particularly like this one. So I'm just going to read it to you first. So we define learning as the transformative process of taking in information that, when internalized and mixed with what we have experienced, changes what we know and builds on what we do. It's based on input, process, and reflection. It's what changes us. And I think looking at some of the key parts of this definition, there's this idea of transforming your knowledge from the experience of the environment to the learner. And then there's this idea of internalizing or representation. So this relates to what we already know, and it takes what we've learned and relates it to the experiences we've had before or in the past. And then there's this idea of reflection, trying to form new connections to this new information. So if we really think about this definition of learning, it has several implications. So this idea of making new connections based on what we know. For example, if you look at the great teachers, people like Richard Feynman, you'll see that they're always helping connect the material that they're teaching to a broad set of positive experiences that the students have had before to really help that internalization process. So if I'm teaching you deep learning, maybe you've already done some machine learning and you've seen maybe aspects of deep learning with neural networks. So you might currently have the idea that maybe deep learning is just more neural networks. And so my job would be to kind of try and change that view, that there's more to it than just multi-layer neural networks. There's actually underlying theory and many sort of foundations and behind it theorems which help us to understand why going deep works and where the field's heading. And relate the knowledge here to all of the different experiences you've had before. So I think one of the best things we can do to study learning is to start by looking at a very strong example of learning, so in particular the human brain, and see how the brain works. And actually a lot of inspiration and mathematical models have come from studying the brain, and a lot of the new advances in the field have come from studying the brain. So the brain is a complex modular structure divided into a right side, the right hemisphere, and a left side, the left hemisphere. And then it's further subdivided into lobes. So the lobes consist of a frontal lobe, and this is important for what we call executive functions, such as memory and learning. And this helps us with our planning, it helps us to sequence, it helps us to think through ideas. And other living beings don't actually have as much of a frontal lobe as we do. They might have more neurons than us, but they don't have this large architectural block which allows all this planning. So that's clearly quite an important part of the architecture for why we've been so successful as human beings. And there's also this parietal lobe, which is shown in this kind of orangey yellow colour. And this is mainly involved in sensation, spatial awareness, and it helps us to integrate the information we're receiving. The temporal lobe is shown in red, and this handles our hearing and our language functions. And then the occipital lobe is shown in this teal colour at the back here. And this receives vision information from the front, and it gets sent along the optic nerves to the back of the brain, and that actually allows us to see. And under the brain is the cerebellum, and that helps us with our coordination and timings. Then we see the brainstem shown in purple here, and the spinal cord in purple. And the brainstem it contains a conduit between the spinal cord and our muscles and sensation, but it also contains our regions for consciousness, for breathing, and for managing our blood pressure. So even just a tiny amount of damage to our brainstem makes us comatose. So the point of showing this is just to really explain that the architecture of the brain is very important. And just as you'll see, the architecture of a deep neural network is very important. So if we kind of look at the main building blocks or components within that architecture, within that ribbon of cortex you saw in the human brain, there are about 86 billion neurons, whereas in contrast, an African elephant has 257 billion neurons on average. So neurons are nerve cells that carry electrical impulses. A neuron has thousands of branches called dendrites. They're those kind of spurry things around the end here. And it has a large central process called the axon. This is the axon, this tail here. And the axon can be short, or it can be as long as several feet, going all the way down your spinal cord and along a limb. And the axon is coated in Schwann cells. These are these sort of cells here. And they're covered with a white glistening material called myelin. And myelin, this helps it conduct electrical impulses that eventually go down and conduct to other nerve cells. So the connection or point of contact between the neuron target and other neurons is called a synapse. Here's a synapse. And in most cases, there's a very, very small gap between the point of contact called the synaptic cleft, where there's the presynaptic membrane, the bit above, contains these synaptic vesicles, the bubbly little things inside. And they're full of molecules called neurotransmitters, and they transmit the signal to a target cell in such a way that it kind of fits together like a lock and key. Specifically, they release calcium from the action potential, and this makes the vesicles dump their contents into the synaptic cleft, and it makes the sodium gates open up, stimulating the target neuron, or the potassium gates open up, causing this kind of inhibiting behavior. But basically, you get these electrical signals coming through the dendrites, and they get summed up where the dendrites receive different weights. So all these different voltage signals coming through here. And this changes this charge or voltage gradient across this membrane here. So all of the voltage accumulates. And if the combined effects of the change in the voltage gradient is just enough at the axon hillock, this neck region here, to meet some threshold, then sodium gates start to open up. So here's where the sodium gates start to open up on this spike of voltage activity. And the voltage starts to get very, very positive until some kind of peak region here. And then the potassium channels open up again. And this causes this plunge as the voltage comes back down again. And this electronically affects the next sodium pump, propagating the signal down this axon here. So you get this kind of spike of electronic activity, and it propagates all the way down the axon to connect to all of the other branches from the other neurons. So what's really cool is that with frequent repeated stimulation, the same level of presynaptic stimulation converts into a greater postsynaptic potential. So just reading the slide. In other words, as a neuron gets a lot of practice at sending signals to a specific target neuron, it gets better and better at sending those signals again in the future. So it's like there's kind of this constant decay, but if there's a lot of activity in a short time, it gets easier to let that electrical activity continue again in the future. So that's what's really happening at the synaptic, in the synapse. So that's kind of the basic function of a neuron. and then there's this complex architecture of the brain. We haven't yet got any theory of how learning occurs in the brain. So imagine, like, just as a sort of example, we took a bunch of these neurons and we stuck them in a shoebox, and we put some sensors, connected to sensors to some of the neurons, and we also put some sort of motors on some of the other neurons, so the shoebox can move around and receive stimuli, inputs. And let's just say we put that shoebox in a horrible environment and in a really nice environment. Is just over time it going to somehow learn to do good things and avoid bad things? Is it just going to learn by itself? So we need some sort of extra or additional theory or hypothesis to answer that question. Which brings us onto Hebbian theory. So I should caveat this and say Hebbian theory, there's been developments in this, but this is and especially if you look at pedagogical literature, it's got there are many advances to Hebbian theory. However, from a neuroscience perspective, Hebbian theory is a very nice, simple theory, which is largely shown to be true in various small brains and architectures. So Hebbian theory is named after Donald Hebb. It was an early hypothesis of learning where Hebb explained in 1949 how learning can occur within cell assemblies. And his postulate in the slide, it can be kind of simplified to a famous mantra, which is that cells that fire together wire together, and cells that fire apart wire apart. So just looking at this picture here to explain Hebbian theory, when the girl sees ice cream and maybe hears the words ice cream, actually there's a pathway in her brain with all those synapses which is getting strengthened because she's seeing ice cream and hearing ice cream within a very short period of time. Maybe she then tastes the ice cream, so she gets this strengthened pathway between her taste, her eyes and her ears. And basically what happens is we're constantly forgetting everything. We constantly forget all of our past experiences, but we then experience new things within a short window of time, which causes those pathways to strengthen. And also those pathways connect back to past experiences that haven't been activated. So this actually, if you really reflect on that and think about that, that explains a lot about how we learn best, under what conditions we learn best. So you can say, like, it's good to have like a diverse set of inputs when we try and learn something. So for example, it's nice to like look at YouTube videos. It's good to take notes. It's good to read a book. It's good to watch lectures as well. Really do as much different activities as you can to receive as many different inputs as you can to really strengthen those pathways over a short period of time. It's why revision is quite important as well if you've got an exam, because you're giving yourself a burst of new information and new inputs and new ways of learning by taking notes and studying in a different medium than just watching a lecture. So we constantly forget, but we re-stimulate ourselves within a short period of window time, re-strengthening these pathways, and that's like one of the main theories of how we learn. Now, like I said, caveat, there's loads of other things like looking at the chemicals in the brain, social interactions, which go beyond this, but it is a kind of fundamental, simple picture which gives us a nice idea of how things work. So let's try and build a very simple model using this. So the most common model of the biological neuron is an artificial neuron, and the fundamental concepts of this were first introduced by Walter Pitts and Warren McCulloch in 1943. So it's a very old model indeed. And the basic model has changed, but it's had a few changes over the years, but it's still overly simplistic and far away from like an actual true neuron as we've just seen. Basically, the synapse strength is modeled as a set of weights at each input. So all of these dendrites here are just modeled as simple weights. And they get summed up here. And then the firing mechanism itself, that action potential you saw, is modeled as a nonlinearity, a nonlinear activation function. And that just models the behavior where the voltage gradient is just enough at that axon hillock region to meet the threshold. And the most common simple model of the firing behavior is the rectifier linear unit, the ReLU. And this is this function here, the max of 0 and x. And it's easy to see that the model doesn't fire until the result of the summation is positive. So you see how anything negative is just a flat 0, but it's got a nice direct proportional linear activation according to the amount of input stimulation if it's positive. So the inputs of the weights can actually be negative. And when the sum of all of these weights is enough to be greater than 0, then it fires linearly and directly proportional to its inputs. That's called the rectified linear unit. And it's a very, very simple model, as you can see, of that kind of activations within a short period of time with the different decays and forgetting and the spiking activity. But it's a model nonetheless, and it's shown to work quite effectively. So just going back into kind of history, in 1957, the perceptron was introduced by Frank Rosenblatt, and this is just a single layer artificial neural network which acted as a binary classifier. And after building a machine, and this is, I would, Google the perceptron machine if you like to see what it looked like. It had loads of wires. In 1960, Rosenblatt presented it to the Navy, and he made several bold claims about it, which the New York Times released an article stating these were the embryo of an electronic computer that the Navy expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its own existence. So there was a huge amount of hype around this at the time, but the hype was very controversial within the AI community. The perceptron was soon proved to not classify many types of patterns, and it kind of contributed to this first AI winter in 1974 to 1980. And this is a period of time where all funding was suddenly cut and everyone just believed AI was just some toy. All of those science fiction books and novels, it was all just seen as this kind of dream, and it's just a toy, it was never going to happen. And then the first AI winter, it ended with the introduction of these expert systems, which were developed and quickly adopted by competitive corporations around the world. These expert systems, they had lots of specialist hardware, a lot of funding came again. But it took until much, much later, in 1986, to discover that multi-layer perceptrons greatly improved the ability to classify more shapes. So multi-layer perceptrons, basically deep layers of perceptrons, deep learning, took until a lot later before people realized this was a way to make these models much more powerful, much more quickly. So anyway, how do we actually train these? And unfortunately, we don't really go anywhere near Hebbian theory in 99.99% of the literature. Instead, what we do is much more simple. We do simple task-specific stuff. That's really where the current state of AI is. So in particular, we have large quantities of artificial neural networks stuck together, and they have limited branching factors, not like in the biological neurons. And then we adjust all of the weights of the layers such as to minimize some well-defined objective function. That's how we're using them. So this takes us to our point in history where the backpropagation algorithm was introduced in 1970. So before backpropagation, most of the features in perceptrons and neural networks were actually hand-engineered. So this would literally be people turning dials and knobs on a machine to adjust all of the weights manually to try and achieve some specific task. A lot of trial and error was involved, and it didn't really work that well. But backpropagation is an algorithm which adjusts the weights of this network, puts them up and down just a little bit in the direction of the gradient of the loss, in the negative gradient of the loss. So it's like this algorithm which, given some objective function, says how to lower or raise every little weight in the network to minimize the overall objective function, the error. So the modern version of the backpropagation algorithm is also called the reverse mode of automatic differentiation. And this was first published in 1970 by Finnish master student Seppo Lineenmaa. And it has some extremely nice properties in terms of memory requirements, and it makes it highly practical. And we'll be discussing that in more detail in the next lecture. So backpropagation calculates the gradient of the loss with respect to the artificial neural network weights. And then we iteratively move those weights a little bit at a time in the direction of this gradient. And we call that gradient descent. And when we do this, we don't actually train on the entire data set for each gradient update. Instead, we randomly, stochastically, sample a small batch of data and train on just that small batch rather than the whole thing. And this is why the common optimization approach for neural networks is called stochastic gradient descent, which uses the backpropagation algorithm to compute these gradients. So AI really boomed in the 1980s with the success of expert systems. Now, expert systems, they're knowledge-based systems, and they require humans to pre-specify lots of rules in a high-level language such as Lisp. And they're still used today in applications like controlling water dams. Some police forces use them to make decisions and things like that. But there was good research funding and investment into specialized AI hardware to support those systems, because they required specialist hardware at the time. Then in 1986, Rumelhart, Hinton, and Williams, they published this amazing paper in Nature, which it used backpropagation. It had multiple hidden layers. It had recurrent neural networks. This paper here. But unfortunately, at the time, there just wasn't the compute. There wasn't GPUs like we have today, or powerful computers to really see it through and to see the potential of it. And there were just a few tiny issues with the choice of activation function. They used sigmoids, which caused the gradients to kind of vanish, and it didn't actually train that well, just unfortunately because of a very small, tiny mistake. Well, not a mistake, just they didn't have the theory that we have today to know that sigmoids aren't necessarily the best activations. And then the second AI winter came with the advent of desktop computers in 1987, and this ended the market for specialized AI hardware because people could train expert systems using desktops, and there's the compute era with desktop computers, and it actually caused a collapse in 300 or so AI startup companies. So AI funding just ceased again, and that was the second AI winter. But there were a few small people who persevered and pushed, crazy researchers trying out crazy ideas, or determined, seeing it through, thinking there's really pushing this forward. So convolutional neural networks, or CNNs, were originally proposed by Kunihiko Fukushima in Japan, and they were not originally very popular. And in 1989, Jan LeCun applied the recently published backpropagation algorithm to train a CNN to classify handwritten numbers. And this is a task modern deep learning researchers still use in developing their architectures. I spend many, many hours of my own time trying to classify handwritten numbers, or trying to generate handwritten numbers. It's a great sort of toy example to build more sophisticated algorithms on. So he kept developing this research, and in 1998 he released a pioneering deep learning architecture, nowadays called LeNet-5. And if you read the paper, you'll see it's very much like a modern deep learning paper. So I've shown an implementation of his architecture here in PyTorch, and it's got ReLUs, it's got excellent choice of nonlinearity, it's got convolutions in the first layers, again a very smart choice, some linear layers here. It's a very modern looking, well suited, good deep learning architecture. And things started to really boom now, and we were moving into the current AI spring, where GPUs effectively started to bloom from computer graphics and video games industries, companies like NVIDIA and AMD. But it wasn't really until the year 2000 that NVIDIA introduced a chip that was capable of programmable shading. So in 2004, the first GPU implementation of a neural network was released by authors at Sungsil University in South Korea. Then in 2006, a GPU implementation of a CNN was released, which was at the time just 4 times faster than its CPU equivalent. So nowadays we get much more improvements than that. Then in 2012, CNNs, convolutional neural networks, they started to get state-of-the-art results in image classification benchmarks, datasets such as MNIST and CIFAR10. So actually in your coursework, you'll be using CIFAR10. So we still use these benchmark datasets today. And then this very important moment came at the end of 2012 when Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton, all 3 of those names are incredibly famous in our field. With people like me and my research group, we're always following them on social media or whatever they're publishing. They won the ImageNet large-scale visual recognition challenge by a very significant margin over the next runner-up. So their architecture is nowadays called AlexNet. It had 60 million parameters, and it's a modern, well-regularized GPU deep learning architecture. And in 2015, the state-of-the-art for ImageNet was a network by Microsoft, and that had over 100 layers. So it became clear that the winning solutions had deep layers, lots of nested layers. This idea of deep learning emerged, that deep layers was important for learning. So this brings us now full swing round into the modern era of deep learning. In 2014, Ian Goodfellow from Yoshua Bengio's group released Generative Adversarial Networks, or GANs. This is where two networks compete against each other without supervision in such a way to generate progressively higher quality data, usually images. And GANs have been steadily improving in terms of visual quality. However, some researchers believe now that we've kind of reached this GAN wave, and the GAN wave is starting to plateau and be replaced by alternative approaches. So we'll be studying GANs, but also we'll be studying a lot of these alternative approaches in this submodule. In 2017, Google Brain released a paper called Attention is All You Need, and this greatly improves training of recurrent neural networks. So their model in the paper is called the Transformer, and this achieves a significant improvement over state-of-the-art language models. So one of the main bottlenecks you get in language models is that the probability of the next word depends on the model's prediction of the previous words. And transformers basically, well, there's this sequential dependency, which is not great for parallelism. But transformers basically allow more parallelism in this setting by computing some attention over a matrix, which allows a network to more efficiently learn from the relevant parts of the sequence. So this kind of increasing parallelism. And the paper was trained on 8 NVIDIA P100 GPUs, and they're very high-end cards at the time. Now we're moving into, in 2019 and 2020, OpenAI and other companies started this massive arms race to train progressively larger and larger models, usually using transformers. And that brings us on to GPT-3, which is trained on the entire internet. And it's trained to predict the probability of the next word conditional on the previous words. So, for example, if you're given a sentence like, the cat sat on the mat, let's say you get to, the cat sat under, then the model tries to predict the distribution over the next token or next words. So it might be like mat or rug or floor. But it tries to predict that distribution where it's likely to output mat or rug or floor. And it tries to not predict the probability of something like suction type 5 Stirling engine. It's not that likely that in a given sentence on the internet you would get the cat sat on the suction type 5 Stirling engine. So at the tails of the distribution, you just start to get random noise and gibberish. But at the mode of the distribution, you start to get quite sensible outputs as you sample around the distribution learned. So the cool thing with these larger and larger language models is they've been shown to start to solve all kinds of tasks involving language. So this is the idea of solving many tasks, or meta-learning, where one model can solve translation tasks. It can, like you saw earlier, it can translate plain English into legalese or lawyer speech and back and forth. It can translate English to French. There's a big push now to see if you can get these models to start doing actual research, like solving mathematical equations. People are trying to use these models to continue writing storybooks. So if your favorite author has just died or passed away, don't worry, because in the future we'll just be using a transformer and we'll be able to synthesize an infinite space of probable books that flow from his writing style. So this kind of max likelihood imitation model, they're very, very exciting seeing what's coming out of this field as we get more and more parameters, and we're reaching a critical point soon where we're going to have the same number of parameters as the human brain. Lex Friedman gives a video if you want to see more about that, about how GPT-3 is progressing, how long it will be based on current energy bounds before we're at a state of the human brain. So how does deep learning overlap with all of these other fields of AI? Well, I hope you'll see that deep neural networks kind of sit at the intersection of many other fields of AI and machine learning. So you can kind of think of it, machine learning as being this encompassing term, and within machine learning we've got deep learning, reinforcement learning, and meta learning. And really many of these methods can use deep neural networks, deep functions within them to improve their performance. So Models can be supervised, they can require labels and annotations, they can be unsupervised, where you don't have that requirement, they can be semi-supervised, where you have some labels and some unannotated data. They can be trained on static fixed data sets, or they can be used as components, for example, in reinforcement learning, where you're actually changing on dynamic and changing data sets, for example, in stock market prediction. They can be trained on one task, such as classifying handwritten digits, or as you've seen, they can be trained on some meta-learning objective function which somehow captures a distribution of tasks. And given some data, like a piece of homework, the model then figures out what task it's meant to do as it reads or takes that data as input, it figures out what its output should be. So comparing deep learning with machine learning, again, I'm assuming you've covered aspects of machine learning in the previous submodules, so I don't really need to talk about how the data distribution can be experienced, but it's worth mentioning that in reinforcement learning we will cover experiencing dynamic changing distributions. So we'll be looking at how agents can make changes in a dynamic environment where they have some agency or control over the environment. Within the deep learning submodule, though, we will just be looking at fixed data sets and the implications of where your training data distribution is not IID, or independent and identically distributed, to your expected task distribution. So if you've been given some data from one distribution, or it's been collected in one way, and then you're testing another set of data which has been collected a different way, there's kind of like this theory of how models will generalize between the two, or in how they will either succeed or fail at generalizing. So we'll be looking deeper at that generalization theory, but with a specific angle on how to generalize within deep architectures. So, I mean, I already gave examples of tasks at the beginning, and you've seen performance measures if you've done any machine learning before, like L2 losses and mean squared error in regression. Often in deep learning, we'll be optimizing for multiple weighted objectives. So we will consider the challenges in kind of balancing all of those various performance measures. With deep learning, we'll be looking at tensors, high dimensional data, how we represent that and sample that. And the backpropagation algorithm in particular will be having a mathematical foundational lecture where we just look at foundational statistics and foundational calculus, and we'll look at the backpropagation algorithm within that. We'll be looking at modeling joint distributions. So this is like a statistical view of generative models, how actually most learning tasks can be thought of as learning a distribution over observations of your data set. We'll also briefly look at how we can interpret the learning problem through a geometric manifold perspective. And we'll look at the theory and the scientific process of actually designing architectures. So there's this very rigorous scientific approach to, given a task, data of some dimensionality and sparsity, what is the right way to go about designing and implementing an architecture to solve that task. We'll also look at regularizing very high capacity neural networks, and basically we will have a very over-parameterized network, but we want to try and somehow smoothen it out so that it fits very well to the underlying task distribution. There's a lot of GPU computing. The tools will be used are very well written such that they can natively exploit a massive amount of parallelism where it's available. We'll look at not just learning one task, but generalizing to a distribution of tasks, which generally you don't go that far with traditional machine learning. And we'll be really going to ground with a deeper, more rigorous and solid theory of generalization. So we'll have an entire lecture just dedicated to generalization theory and designing architectures and so on. And we'll be, once all of that underpinning foundational work is done, we'll have quite a few lectures where we just look at recent state-of-the-art advances, reading papers, looking at the methods and seeing where things are going. Because honestly, there's just a huge amount of new emergent ideas which it's very hard to keep track of. So we'll focus on sort of very popular big emergent papers, so that after this course you've got the foundations, but you've also got a rich insight into what's around you and what you can use and how to use it and apply it. One common misconception I'd like to correct early on is that a lot of people say deep learning is just a black box. We don't really know what's going on. But actually there is a lot of rigorous theory into deep learning, and it's not actually just the black box. There's statistical learning theory, generalization theory, Vapnik-Chevanenkis theory. There's all kinds of theorems we can use and apply to see and know why going deep is effective. We have proofs to show under various conditions how it's still a universal function approximator, how it generalizes, and why regularization is important, and so on. So we are actually getting, as a research community, to a much richer and deeper understanding of this field. It is a bit mathematical to really comprehend why going deep is effective. But we shouldn't just be saying it's just a black box, we don't have a clue what's going on, because we really do. It's just a bit complex to explain, and it takes a bit of time. So we'll be looking at a lot of the theory of why it works and how it works and how to generalize, how to design. So just reading through this slide, in summary, deep learning has a lot of overlap with many areas of AI, and it achieves state-of-the-art in many ill-defined tasks. Especially in cases of very high-dimensional data, like large images, audio signals, and so on, with huge data sets, like the internet itself. And it's very, very parallelizable. A lot of the advances has been due to parallelism and advances in computing. Deep learning has a lot to do with statistics. The calculus isn't so important, but the kind of statistical view of it is quite important. And it has a bit to do with geometry as well. So if you're confident with your geometry, it gives you another lens or angle to look at the deep learning problem. And it's a rapidly growing, expanding and evolving field, so it requires a refresh every year to really keep up to date with it. Keep looking at Twitter and various communities where you can keep up to date with all of the recent research coming in. So yeah, that concludes this first lecture. I hope you found it interesting and the examples and the advances in the field as exciting as I do. I always really find it a privilege to teach deep learning, because as learning about learning is, I think, one of the most exciting and rewarding things we can be doing as human beings. And as a researcher in this field, just the fact that we can try a new idea out very quickly, test it on a cloud server, and maybe we've now got a new, unique way of understanding some of the underlying patterns and structures of, say, nature itself. So it's a very exciting field to be in, which changes very quickly. Anyway, that concludes this lecture. Thanks very much.